So let's restart. Now we are going to focus on the shear design. So shear transfer in partially cracked beam section with web reinforcement. So as earlier we have studied that the minimum web reinforcement, that is non-pre-stressed reinforcement, will be provided in the pre-stressed concrete beams. And along with that, we studied that preferably longitudinal bars of small diameter should also be provided to increase the resistance to the pull out. So now let's see this figure. So this is the cross section of the beam, and you can see this is the shear reinforcement being provided in the form of the U-shaped stirrup. This is the longitudinal section, and in the longitudinal section you can see a part of the beam has been shown longitudinally, which includes the crack. So this is simply supported beam. These are the shear stirrups. These are the shear stirrups, which are provided at a spacing S. So these are the stirrups provided at spacing S. D is the depth of the section. D is the depth. Fine. Then we have this VP and PE. This we will discuss because this VP is basically PE sine theta, effective pre-stress. We find the component of the effective pre-stress which is taking part in resisting the shear. So let's start. If preferably you can make this figure, it will be much more easier for you and much more easier for us to explain and discuss. So the forces acting on a part of the beam, between the diagonal cracked section and the adjacent support. So this is the adjacent support, this is the diagonal cracked section. Vertical U stirrups are shown. These are the vertical U-shaped stirrups, and in the longitudinal these stirrups are shown, which are provided at a spacing S. We will also discuss this V shear A, Y, C, X, C, Z. These are basically the components which we will discuss in a short while. Because of the presence of the longitudinal compressive pre-stress in the concrete, the slope of the diagonal crack is generally flatter than 45 degrees. So because of the presence of longitudinal compressive pre-stress, so at the start of the lecture we said that in pre-stressed beam there will be pre-stressed compressive load. So pre-stressed compressive load, that is, it is producing a hog in the pre-stressed beam. Hog means that you have compressive stresses at the bottom, and tensile stresses at the top. So because of the presence of the longitudinal compressive pre-stress in the concrete, the slope of the diagonal crack is generally flatter than 45 degrees. It means that instead of having the web shear crack, we are going towards flexure shear cracks. So flexure shear cracks will be more common. Flexure shear cracks, they are flatter and they are inclined at angles smaller than 45 degrees, and you can say they are more or less parallel to the longitudinal axis. So it is assumed quite conservatively that the horizontal projection of the crack has the length D equal to the effective depth of the beam measured to the tendon centroid of the section. So I repeat, the cracks are generally flat, that they are parallel to the horizontal, ठीक है जी. So it is assumed conservatively that horizontal projection of the crack has length d. So the length of the crack has been taken equals to d, where was d was the you can say effective depth of the section. ठीक है जी. So the length of the crack, horizontal projection of the crack has been taken equals to d, that is the effective depth of the section. Everyone agrees to this point? ठीक है जी. So it is quite conservative that the horizontal projection of the crack has taken length d equal to the effective depth of the beam measured to the tendon centroid of the section. If the spacing of the web reinforcement, कितनी है जी? S. So this is S. The spacing between the U-shaped stirrups in the web part. So it is assumed, if the spacing of the web reinforcement in the direction of the member axis is S, the number of U-shaped stirrups crossing the diagonal crack is D over S. D क्या है? It is the horizontal projection of the crack. S is the spacing between the stirrups. ठीक है जी. So it means the number of U-shaped stirrups present in the diagonal crack is D, the horizontal projection of the crack. S is the spacing of the U-shaped stirrups. So the number of U-shaped stirrups crossing the diagonal crack is D over S. This point everyone agrees. This is the effective depth, and the horizontal projection of the crack has been taken. The length of the horizontal projection of the crack has been taken equals to the D, that is the effective depth of the section. S is the distance between the U-shaped stirrups. So number of U-shaped stirrups in the crack, in the horizontal projection of the crack length, D is D over S. ठीक है जी. So you can see in this length you can have 1, 2 and 3 stirrups, D over S. So when the member is at the incipient failure, the stirrups are stressed to their full yield strength. So this is an assumption based on the experimental and research results that when the member is at the incipient failure, the stirrups are stressed to their full yield strength. The stirrups are stressed to their full yield strength, that is Fy. ठीक है जी. Full yield strength and their contribution, the total contribution of the stirrups to transfer of shear stresses across the crack section is AV. AV is the area of the one shear stirrup. AV is the area of one shear stirrup. Fy is the stress. So area into the stress will give you the load. ठीक है जी. Area into the stress will give you the load. ठीक है. D over S will give you the number of stirrups. Number of stirrups in the cracked section. So I repeat, the total contribution of the stirrups to transfer of shear stress across the cracked section is Vs, the contribution of the steel, that is contribution of the steel to resist the shear is AV. AV is the area of one stirrup. Fy is its stress, which is taken as yield stress. ठीक है जी. So stress into area will give you the force. ठीक है. And D over S is number of stirrups crossing the crack or present in the crack section. So Vs is AV into Fyo into D over S. So everyone agrees with this formula, because this formula you guys have used multiple times in your shear design at your undergraduate and in your reinforced concrete design as well. ठीक है जी. So AV is the total steel area of one stirrup. ठीक है जी. Stirrup, that is 2 times the bar cross sectional area, because you are providing U-shaped, what you say, stirrup. So this area will be considered twice, 1 and 2. ठीक है जी. Everyone agrees to this point? Everyone agrees?
Yes, sir.
Okay. So AV is the total steel area of one stirrup, that is 2 times the bar cross-sectional area for the typical case with U stirrups. ठीक है जी. So contribution of the steel in resisting the shear in the crack zone is AV, area of the one stirrup, times the yield stress, gives you the force, into ds gives you the total number of what you say, stirrups in the cracked section. Area of one stirrup is because we have U-shaped stirrups, so area will be 2 times the bar cross-sectional area for the typical case with the U stirrups. Okay. Fine. Now, next is the tendon centroid crosses the crack section at slope theta. Now, if you see this, this is your tendons. ठीक है जी. We have what you say, this is an example of the tendon with variable eccentricity. So you can see the tendon crosses the section at an angle theta. PE is the effective pre-stress. PE क्या है जी? It is the effective pre-stress. PE is the effective pre-stress. So if the tendon centroid crosses the cracked section at slope theta, ठीक है जी, then the tendon transmits a shear force. Tendon transmits a shear force equal to the vertical component of the pre-stressing force. So this is the vertical component, VP. ठीक है जी. This is the effective pre-stress which is at an angle theta and where it is crossing the crack section. So the vertical component of this has been taken as VP. ठीक है जी. The vertical component has been taken as VP. So if the tendon centroid crosses the cracked section at slope theta, then the tendon transmits a shear force equal to the vertical component of the pre-stressing force. ठीक है जी. Vertical component of the pre-stressing force. Although the tendon force increases as the member is overloaded, it will be conservatively assumed equal to the effective pre-stress. ठीक है जी. It is conservatively assumed equal to the effective pre-stress. Thus, the vertical component of pre-stress is effective pre-stress into sine theta. ठीक है जी. So you can see your tendon is inclined at an angle theta. ठीक है. And this is the effective pre-stress. The vertical component of effective pre-stress is this one, VP, which is taken as PE into sine theta. Agrees with this point? So although the tendon force increases as the member is overloaded, however, it will be assumed conservatively equal to the effective pre-stress. Thus, the vertical component is VP is equal to effective pre-stress times sine theta. ठीक हो गया जी? Agree? This was the contribution of the what you say, the non-pre-stressed steel, which is provided in the pre-stressed what you say, beam. ठीक है जी? So this is the contribution of non-pre-stressed steel provided in the web of the what you say, pre-stressed beam. This is the contribution of what you say, the effective pre-stress. ठीक है जी. If the tendon centroid crosses the cracked section at slope theta, then the tendon transmits a shear force equal to the vertical component of the pre-stressing force. Although the tendon force increases as the member is overloaded, but conservatively it is taken equal to the effective pre-stress, and the vertical component has been calculated as PE times sine theta. A third contribution to the shear transfer comes from the frictional resistance. ठीक है जी. Now third contribution क्या है? This third contribution is from the frictional resistance along the naturally rough surface formed by the crack. So whenever there will be a crack, ठीक है जी, a surface will be formed, and that surface will provide some resistance. So third contribution to the shear, ठीक है जी, comes from the frictional resistance along the naturally rough surface formed by the crack. So this is the crack, ठीक है जी. So this surface formed has some internal resistance to the shear. This is the crack, ठीक है. This crack is basically having some internal resistance to the shear. So a third contribution to the shear transfer comes from the frictional resistance along the naturally rough interface formed by the cracks. Tests have confirmed that a significant redistribution of internal forces takes place upon cracking, such that such that some tendency to slip exists along the interface. This is resisted by the roughness of the cracked surface and the interlocking between the aggregates. ठीक है जी. The resisting force, internal resistance force due to the roughness of the surface, that is VA, associated with aggregate interlocking, acts on the free body in the direction indicated in the figure. ये फिगर है, और इसका जो वर्टिकल कंपोनेंट है, this is the resistance due to the slip surface along with the aggregate interlock VA, and its vertical component has been taken as VAY. This VAY. ठीक है जी. So पहला आपका क्या था? Vertical component of the shear reinforcement AV into FY times D over S. Second was VP, the effective pre-stress component in the vertical direction. The third one is the contribution of the fracture surface in resisting the in providing the resistance. ठीक है जी. And its vertical component, this is VA, and its vertical component is this VAY. A third contribution to the shear transfer comes from the internal resistance along the naturally rough interface formed by the crack. Tests have confirmed that a significant redistribution of internal forces takes place upon cracking, such that some tendency to slip exists along the interface. This is resisted by the roughness of the surface and the interlocking of the aggregates. This resisting force VA associated with aggregate interlock acts on the free body in the direction indicated in figure, which I have shown. So its vertical component is VAY. ठीक है जी. Internal resistance and aggregate interlock, its component is VAY. The concrete in the uncracked compression zone above the diagonal crack provides a resisting force. So if you see this one, so this is the crack. So the portion below the crack is the crack portion, and the portion above the crack is your uncracked section. So now this uncracked section, the concrete in the uncracked compression zone above the diagonal crack provides a resisting force that is VC V subscript CZ. Now there are now four forces contributions. One was the contribution from the U-shaped stirrups. The second was the contribution of the pre-stress, which is inclined at an angle theta passing through the crack. Okay. The third contribution was from this internal resistance and the aggregate interlocking. Its component was this VAY. And the fourth one is the contribution from the compression zone of uncracked section. ठीक है जी? So everyone agrees with these four contributions. If you have any question about these four contributions, please ask me. Is this clear? Is this point clear? Because this is important, because this forms the basis for the, what you say, shear design. Usama Khan, is this clear? Hassan Akhtar, is this clear?
जी सर.
Mohammad Firoz Khan.
Yes sir.
Okay. So first contribution from the non-pre-stressed U-shaped steel stirrups, ठीक है जी, passing through the crack section. Second is the contribution of the tendon centroid, which is inclined at an angle theta. Third is the contribution of the surface roughness and aggregate interlocking. And the fourth is the contribution of uncracked compression zone above the diagonal crack, which provides a resisting force VCZ. Shear force that is shear force that is subscript CZ, compression zone, uncracked compression zone. Now, summation of the vertical forces equal to the zero leads to the shear strength. Now, shear strength is provided by AVFY d over S, that is the contribution of the non-pre-stressed U-shaped steel stirrups. VP is the what you say, contribution of the tendon pre-stress, which is inclined at an angle theta passing through the crack, which is PE sine theta. Then contribution of the aggregate interlock and the slip surface. So this is VAV, VAY, and this is the contribution of what you say, contribution of the uncracked compression zone above the what you say, crack. Contribution of the concrete compression zone above the crack. In spite of the, now these are four contributions. So in spite of the intensive research over the years, the exact values of the contribution of the aggregate interlock and fracture plane and contribution of the uncracked compression zone above the crack have not been known. ठीक है जी, in spite of the intensive research over the years, the exact individual contributions of VAY and VCZ. VAY, the contribution of the fracture plane and the aggregate interlock, and contribution of the compression zone above the crack are unknown. Okay? So from tests, a very conservative assumption is made that the combined contribution of VAY and VCZ ठीक है जी, is not less than VC. VAY is the contribution of the fracture. This one is the contribution of the, what you say, roughness or roughness of the surface and aggregate interlock. And VCZ is the contribution of uncracked compression zone. So the sum of these two, VAY and VCZ, their contribution is not less than VC. ठीक है जी, that shear force that caused the diagonal crack to occur. So now instead of individually finding the contribution of the fracture plane and roughness of the fracture plane and aggregate interlock and what you say, crack compression zone above the crack, they are not exact values are unknown. So conservatively we are taking them equal to the shear strength of the concrete. We are conservatively taking them equal to the shear strength of the concrete is not less than VC, the shear force that caused the diagonal crack to occur. The magnitude of VC, the magnitude of the VC may be determined either by the web shear cracking or flexure shear cracking. So based on two types of cracking which we have discussed at the start, that is flexure shear cracks in which you have more flatter or more horizontal cracks as compared to the web shear cracking in which we have more 40 cracks at the 45 degrees. ठीक है जी. So the magnitude of VC, the contribution of the concrete in resisting the shear can be determined either by considering the web shear or flexure shear. So from now onward, we will be considering the contribution of concrete. We will be taking all these as contribution of the concrete. ठीक है जी. And in the concrete, we know that there are two possible failures. One is flexure shear cracking, which is more ductile as compared to the web shear cracking, which is more brittle and in which the cracks are at 45 degrees. If in addition, the vertical component of the pre-stress force is neglected because the angles of tendon slope in the cracked section, then the ultimate shear strength will be equal to, so what we are doing, we are considering this, the contribution of the U-shaped steel reinforcement. This VP, we are going to ignore it because the angle of inclination of this tendon, that is very small. And this VAY, which is the contribution of the fracture plane and the aggregate interlock, and VCS, contribution of uncracked compression zone above the crack, this we have considered equal to VC. So after this, now after assuming these two things, now we have what you say, the nominal shear strength expression as contribution from the steel plus contribution from the concrete. So if what we are doing, so we have taken the contribution of U-shaped steel as it is, VP, which was the vertical component of the pre-stress force. We have ignored it because the tendon slope is very small. VAY and VCZ, the contribution of the fracture plane and aggregate interlock, and VCZ, compression zone above the uncracked uncracked compression zone above the crack. ठीक है जी, its contribution has been taken equal to, conservatively taken equal to VC. Now the revised or updated expression to compute the ultimate shear strength will be equal to contribution of the U-shaped steel plus the contribution from the concrete part. So everyone agrees with this equation because in our design and in our what you say numericals, we will be using this expression to calculate the ultimate shear strength. If you have any question, please ask me now. Everyone agrees to this?
Yes, sir.
Okay. Now next comes if the excess shear above if the excess shear above that which is resisted by the concrete is identified as nominal shear minus VC. ठीक है जी, VC is the contribution. Now if you see over here the nominal shear, it is the sum of the contributions of the U-shaped stirrups, ठीक है जी, U-shaped steel stirrups plus concrete. So this is the two contributions. Now if the excess shear above that which is resisted by the concrete is identified as ultimate shear strength minus the contribution of the concrete. ठीक है जी? So this will give you basically the contribution of steel. ठीक है जी? Because the actual is now shear strength is equal to sum of the contribution of steel plus contribution of concrete. So, is resisted by the concrete is identified as nominal shear, ultimate shear strength minus the contribution of the concrete. This will now give you remaining as the contribution of the steel. And if the web reinforcement ratio is defined, reinforcement ratio we define as area of the shear reinforcement divided by the width of the web into the spacing. ठीक है जी, into the spacing of the shear stirrups. So reinforcement ratio, shear reinforcement ratio is defined as area of the shear stirrups, ठीक है जी, divided by the width of the web into the spacing of the stirrup. So this is your reinforcement ratio. Then we can simplify this. Rho Fy is equal to nominal this ultimate shear strength minus the contribution of the concrete over Bw into D. ठीक है जी? So this will give us then what you say the contribution of the steel. So over design basis based on the ACI code is that the design, you can say design shear strength 5EVN, which will be sum of the nominal shear strengths provided by the steel and the concrete, its sum into the strength reduction factor phi. It should be equals to or greater than the applied shear. It should be equals to or greater than the applied shear. So this is the general design requirement which we have been studying in all the design subjects, that phi Vn design shear strength should be equals to or is equal to or greater than the applied shear. Vn without the strength reduction factor, it is called as the nominal shear strength, which is the sum of the nominal shear strengths provided by the concrete and steel. ठीक है जी? So this contribution nominal shear strength, this should be great nominal shear strength, which is the contribution of the steel and the concrete. So after it's multiplied with the phi, it becomes the design shear strength. So this design shear strength should be equals to or greater than the applied shear. So the design of cross section subject to the shear is based on the relationship that phi Vn is equal to or greater than Vu. The nominal shear strength Vn is computed as the sum of the nominal shear strengths provided by the concrete Vc and the steel reinforcement Vs. So design basis, so nominal shear strength is sum of the contributions of the shear contributions for the concrete plus the contribution from the steel. The first critical section for the shear is assumed to be at a distance h/2 from the face of the support, from the face of the support. ठीक है जी, the first critical section for the shear is assumed to be at a distance h/2 from the face by the support. One thing I want to make it clear, this point which we discussed, diagonal tension crack which we said is at a distance of, one second please, I want to clarify this point so that it's not mixed up. This, we are talking about the diagonal tension crack, ठीक है जी, from where your diagonal tension crack originates, that is quarter point of the span. This point which we are talking here, this point which we are talking here, it's the critical section for the shear, and this critical section for the shear is assumed to be at a distance h/2 from the face of the support, h/2. ठीक है जी, it's the critical section where the shear is, you can say, is large, ठीक है जी, is at a distance h/2 from the face of the support. So next is, there are some formulas which I want to quickly go through so that next time when we do the numerical, we have an idea that how to use them. We should know all the components of it. So shear design criteria based on the ACI code. So nominal shear strength provided by the concrete, because we said that the nominal shear strength will be provided by concrete plus the nominal shear strength provided by the steel. The concrete part comprises basically VAY and what you say, this and VCZ, uncracked compression zone, which we have conservatively taken them equal to VC, and this VP we have ignored. So the value of VC is to be taken equal to smaller of VCI, which is the shear force that would be required to produce the flexural shear failure, which is required to produce the flexural shear failure. Because in the concrete, there can be two failures possible. One is the flexural shear failure and other is the web shear cracking. So web shear failure or flexure shear failure. So the value of VC is to be taken equal to the smaller of VCI, that is the shear force that would be required to produce flexure shear failure, and VCW, shear force that would produce web shear cracking, that would produce web shear cracking. So VCI is equal to 0.6 times under root FC prime into BWD, BW into D. D is the effective depth, you can say, from the compression force to the point of the pre-stressing steel. BW is the width of the web part. FC prime is the design compressive strength. FC prime, V naught plus VI over M maximum. These are basically your what you say, factored shear and bending moment. MCR is the critical bending moment. So BW is the width or the web width. In our case, it will be the web width. D is the depth from the compression phase to the centroid of the pre-stressing steel. VI and M maximum, this ratio are the factored shear and bending moment at the section considered. V naught is the shear due to the self weight, and MCR is the cracking moment, is the moment causing flexure crack or cracking moment. ठीक है जी. So please note down this formula for VCI, which is VCI, because the value of VC, the contribution from the concrete side, has to be taken smaller of VCI and VCW. So first we are considering VCI, which is the shear force that would be required to produce the flexural shear failure or flexure shear crack, that is zero point 0.6 times under root FC prime into BW into D plus V naught plus VI over MX into the MCR. MCR is your cracking moment. This is VI over M maximum. These are the factor shear and bending moment at the what you say considered at the section consider or at the cracked section. ठीक है जी. V naught is the shear due to the self weight. D is the effective depth. BW is the web width of the flange. Web width. FC prime is the design strength, and 0.6 is the coefficient. Everyone noted down this formula. Please note down this formula.
Okay, sir.
Yes, I'm waiting for you guys to. Okay, now let's move forward. Now, V naught is the shear due to the self weight, and MCR is the cracking moment. Now, to compute this moment, IC over C2. IC आपका क्या है? It's the moment of inertia of the your what you say, moment of inertia of your cross section of the pre-stressed beam, IC. C2 is the distance from the neutral axis to the tensile side of the concrete. ठीक है जी, bottom part of the I-shaped section. Then F2P, these are basically your tensile stresses at the bottom face. F naught is the flexural stress at the bottom face resulting from the self weight of the member. VCI needs not to be less than 1.7 under root FC prime BWD. So the value of VCI needs not to be less than, minimum is 1.7 under root FC prime BWD. ठीक है जी? Everyone, please note down this point that the VCI needs not be taken less than 1.7 under root FC prime into BWD. The nominal shear strength corresponding to the web shear cracking VCW is 3.5 under root FC prime plus 0.3 times FCC into BWD plus VP. ठीक है जी, VP is the same, which is the vertical component of the effective pre-stress force, which is effective pre-stress force times the sine theta. D is the effective depth. BW is the width of the web. ठीक है जी, FCC is the confined concrete strength. FC prime is the design strength, and VCW is the nominal shear strength corresponding to the web shear cracking. And here we said that the value or the nominal shear strength provided by the concrete, its value should be taken equal to the smaller of VCI and VCW. This is the formula for the computation of VCI, that is 0.6 under root FC prime BWD plus P naught plus VI over MX into M critical. And this VCI needs not to be less than 1.7 under root FC prime BWD. Then the nominal shear strength corresponding to the web shear cracking VCW is equal to 3.5 times under root FC prime plus 0.3 FCC into BWD plus Vp, where Vp is the vertical component of the effective pre-stress force. Then comes the contribution of the steel reinforcement, shear reinforcement. So when shear reinforcement perpendicular to the axis of the member is used, its contribution to the shear strength is Vs is equal to area of one stirrup into the yield stress into d over s, that will be number of stirrups in the crack section, number of stirrups in the crack section. So Vs is the contribution of the shear reinforcement in resisting the shear, that is Av times Fy into d over s. The shear reinforcement Vs perpendicular to the axis should not be taken larger than 8 under root Fc prime BWD. Please note down this point. Noted this point? Now, the total nominal shear strength is found by taking the summation of the contributions of the concrete and the steel. So this is the contribution of the steel part. This is the contribution of the concrete part, which should be smaller of VCI and VCW. Design requirement is that design shear strength should be equals to or greater than applied shear. So the minimum is that the design shear strength is equal to the applied shear. So applied shear is equal to phi, that is the strength reduction factor, into the contribution of the steel plus contribution of the concrete, and this should be equal to phi times area of shear area of the used shaped stirrup into the yield stress into d over s plus Vc, and this one, then the required cross-sectional area of one stirrup, the required area of cross-sectional area of one stirrup is very clear. Vu is the total applied shear. This is the contribution of the concrete. So total shear minus the contribution of the concrete will left you with the contribution of the steel. ठीक है जी. So S over phi Fy into D, this will give you the total area of the stirrup required, total area of the stirrups required to provide the required shear, to provide the required contribution of the shear to provide the required contribution of the steel to resist the required shear. So in practical, a trial stirrup size is found using by computing S, the spacing. So phi into area of the stirrup. Generally, you know that this dia of the stirrup is taken as 9.5 to 15. So commonly we take 9.5 or 12.7 millimeter dia. So we can phi, we can calculate the dia of the one stirrup into the yield stress. Yield stress is generally 250 megapascals. D is the depth which you will get from the cross section detail. Vu will be your applied shear. 5Vc will be the nominal contribution of the concrete in resisting the shear. Okay, so then there are two formulas which are given to ensure that the web reinforcement which you calculate should not be less than these two critical values. So minimum web reinforcement is taken as smaller of the following two values. AV, area of the shear reinforcement, should be equal to 50 times BW into S over Fy. ठीक है जी. BW is the width of the web, S is the spacing of the stirrups, Fy is the yield strength. AV, the second is area of pre-stress, FPU is the ultimate tensile strength, Fy is the yield strength, S is the spacing, D is the effective depth, D is the effective depth, BV is the width of the वेब। ठीक है जी। सो next time inshallah we will do the numerical in which we will do the shear design for the pre-stressed concrete beam. If you see, it's quite simple. What we need to do, we need to calculate the contribution of the concrete and the steel. Contribution of the concrete should be smaller of VCI and VCW, so we have the formulas to calculate the contribution of the concrete VCI and contribution and VCW. ठीक है जी। Then the contribution of the steel can be simply calculated VS over ABFYO into D over S. And at the end, we have to ensure that the shear reinforcement which we are providing should be having a value greater than the minimum web reinforcement. If our value is coming less than the minimum web reinforcement, then we will provide the minimum web reinforcement, which will be the smaller of these two values. If you have any question, please ask me now. Ji, someone is typing. You can, ji. If there is no question, then we will stop the sharing and we can stop the recording.